Well, John.
Hello.
Late. More things. Look tired.
Yeah, I'm very tired, but I'm okay other than that.
Okay. Yeah.
Hello, Professor. Hi, Giorgio.
Hey, how are you? Hanging in
Good,
there?
and you?
Pretty good.
We don't have anyone in the classroom. Like, I mean, the physical classroom.
Maybe everybody's tired today.
I think this is the time of the semester where everyone has something or the other going on and it's sort of too much.
Mhm.
Yeah.
Like, including the instructors.
This is maybe one of the first times I felt like I don't have enough time in the day. Normally I'm pretty good about making time for stuff with my schedule, but man, I just feel like I don't have enough time.
Like you really, the Alia is also another example. Like, I don't know how you deal with family and studies and you do a job and studies.
Yeah. I can't imagine having children right now. Oof, I would be struggling. Especially because they're not in the standard system either, where they can just, you can send them to school and do your own thing. You kind of have to do everything from your house, make sure that they're there for their class time and they're with you during your class time. And I'm sure when you're trying to get things done, they're there.
Yeah.
Very difficult. I don't have to worry about that, but
Someone's trying to get into the door, but it's not opening.
there's Luke. Luke.
Give me a second. I think someone is trying to come in.
Have you guys finished the exam yet?
No. We were looking at it a bit last night.
How did that go?
Okay, but not great.
Yeah.
So I was telling someone else yesterday that I think since homework 8 or something, like that's when I think people started giving up. So you can submit any of those until December 4th, like until, so you can use Thanksgiving holidays so that it might give you some room, but I also feel that it kills your holiday. That's some relaxation you could have had if you had given up the whole thing, but it's up to you guys to decide.
Well,
Enjoy your holidays too. So everything has, so all the submissions are available until December 4th, but that's the limit. From that point on, I cannot.
I think Thanksgiving is one of those holidays that's more of just it's not as important of a holiday for me. I think it is a good time to relax, I suppose, but I guess since I've been back in school, I haven't really had that chance.
I think that's the way I was trying to tell, mainly you look for a set of days where you can recapitulate, I think that recharge yourself. And these kind of postponements fills up those days also. And I mean, even though you will end up relaxing on those days, you will be under the stress that, oh, I have to finish, I have to finish. And most often what happens is that neither do you finish, neither do you enjoy the holidays.
I think making that later for the student who is interested in time management and not just postponing. If you chose to just postpone, then the student that's actually, I think most people are behind, but I think the students that are actually behind but orient their time correctly, it's beneficial for them. And I think waiting towards those students is probably better than waiting towards the students that just see it as an opportunity not to do anything.
Yeah, good point. Good point. So that's hopefully that's how it's going to be taken, and it doesn't hurt me at all. So it's just that I don't want to spoil someone's holidays. That's all.
And actually, if I didn't do anything over the holiday, then I would return from the holiday out of whack, like I can forget things that you said a lecture prior if I don't review them. So I think it's good practice to not just give up and sit in your bed for a week. Well, how long is the Thanksgiving holiday? I haven't actually looked at it.
Almost 10 days. I mean, I think it's 9 days, 7 days plus 2 days of that next weekend. So it's 9 days. You come back on 30th. 20th is the last class, and then you come back on 30th. That is just 5 days of classes after that. Okay. Where's Moses? He asked me a question yesterday, and I thought I changed my strategy for the course, and he's disappeared. So, okay. So, yeah. So I haven't posted the homework yet and the final exam. So I'm supposed to announce that, but I forgot to bring the file, which I usually write down these things. So there will be a homework that will be due on next Thursday, and there will be another homework that will be due on the last week of classes Thursday, and there will be a final exam. So that's the things remaining now. We want to do today. I want to do Bessel functions, or introduce Bessel function. I was planning to do spherical harmonics and things, or Legendre polynomials, and do details of that, which we will try to cover in the last week. But I decided to do Bessel functions after the discussion we had at the end of class yesterday. With I think not everyone was involved in that. Probably Moses was there, and those were in the class that were. So let's give the title of today as Bessel functions. And I will motivate it from the Green's function in electrodynamics or electrostatics, let's say. How many of you have, let's begin by saying, how many of you have heard about Bessel functions?
You did a brief section on Bessel functions in my undergraduate mathematical physics course, but it wasn't anything very extensive, I guess you could say.
Okay. And how many of you have used Bessel function?
I have.
You have, yes. And in what context?
We used them in my E&M course in Kansas, but that was a few years ago, so I don't really remember.
Good. So, so a simple way of saying it is that if you're doing any of the problems, there is a good chance that if you have a spherical symmetry or cylindrical symmetry, one of the coordinates, typically you have 3 coordinates, right? So let's say if you have, let me write this down. So if you have spherical symmetry in a problem, then typically you would use r theta phi. One of the coordinates, typically r, will satisfy the Bessel differential equation, or it will be given in terms of Bessel function. So r will involve, this is called spherical Bessel functions. There are various kinds of Bessel functions. So this is most probably, this is how you will encounter Bessel functions. You're trying to solve a system. It could be an electrostatic configuration or any other configuration, and you're trying to solve a spherically symmetric problem, and you write a differential equation for R, and the solution for that will be given in terms of what is called spherical Bessel functions. That's not what we are going to do, but it's given in terms of what we are going to do today. Even if we have cylindrical symmetry, or for that matter, even if you have a planar symmetry that we did for dielectrics, right? A planar symmetry can be done in terms of rectangular coordinates x and y, like in the plane, or you can use cylindrical coordinates rho and phi. And again, that will involve this rho, phi, and z. And the rho coordinate in this will involve not spherical Bessel functions this time. This time it will be exactly in terms of the Bessel function. So that's motivation. That's where you can expect to see Bessel function. I also want to take this example to show 2 things. One is, most of the times when you're introducing a function like Bessel functions, earlier we had legendary polynomials, these all form complete set, like Fourier functions are another example. And most of these quantities are defined in terms of what is called a generating function. First, you have to define them. So the standard idea is, at least the traditional approach is what you call a generating function, and you have a series representing the function, and then everything is done in terms of the series. For example, if I were to ask you to prove that derivative of sine theta is equal to cosine theta, I suppose I were to ask you to prove that, you will most probably do what the definition, you need the definition of sine theta, right? And what's the definition of sine theta, by the way? Suppose I were to ask you this. How would you think of sine theta? If I were to ask you to define sine theta, like prove that derivative of sine theta is cosine theta.
In terms of, E minus E.
That's a good point. Yes, you can write it in terms of exponentials, but that's a good, like that's how typically you do. Now let's say, what if I were to ask you to show that the derivative of exponential is exponential itself? Like you wrote sine theta in terms of exponential, then you go to exponential. Typically, a function is given in terms of its series. You often call it the power series. If you know the series, then you know the function. So everything you want to prove related to the functions, usually identities, there are sine theta 1 plus sine theta 2. Those identities make a good toolbox for you. At some stage, you have to prove them, and not many identities are available for most of the functions that you can define. For example, you don't have as many identities as trigonometric functions or Bessel functions, but Bessel functions are still very well studied. It is one of the most useful functions, so it has lots of identities available for it. But having said that, so what I'm trying to say is that a function like Bessel function is defined in terms of a series, which we will define most probably today or in the next class. It is also can be given in terms of an integral. And a more modern perspective is to prove everything using integral representations instead of using a series representation. So those are two different views we will see. And I'll begin by pointing out what's the integral representation of Bessel function. Do a little bit of that, and probably most of your homework will involve using the series representation of a Bessel function. So that's something I plan to do. Okay, so how do we motivate this Bessel functions? Remember that electrostatics involves the Green's function or a point charge, right? We know that in electrostatic, either the electric potential, right? Electric or gravitational, right? Gravitational. Like historically, it was the gravitational potential that led to that, but since you guys are taking electrodynamics, it's if you think of it as the electric potential is phi of r observed at point r is equal to 1 over 4 pi epsilon naught times q over r as r prime. Correct. And we would answers historically, if you see people wanted to, the moment they realized that you can explain the motion of planets using this equation, it was a big deal. So everyone started working out studying every nook and corner of this function, if you want, of this potential, so that you can solve problems that you couldn't solve earlier. So that's the context in which all these studies were made. So let's not write this as the electric potential. If I were to set Q is equal to 1, just let's motivate this. So we have Maxwell's equation, right? Del dot with epsilon E is equal to rho, and del crossed with E is equal to 0. That's electrostatic equation. And so this implies that electric field can be written as negative gradient of the electric potential. Substitute that in there, and I get del square, because epsilon naught is a constant, no material involved. So epsilon naught times phi r is equal to rho. What is this equation called? That's called the Poisson equation. If you have rho not 0, that's called the Poisson equation. So let me write that down.
Is this a special Laplace equation?
Tell that again?
Is it just like a special version of the Laplace?
Yeah, let me tell you what the difference is. Just a nomenclature. I haven't stressed on this since beginning, but you should know the nomenclature. Now, what is Laplace equation? Laplace equation is a homogeneous version of this. If it is equal to 0, so there is no charge at all, and often there are regions where there is no charge, so that's called the Laplacian. And if you have a source on the right side, it's called the Poisson equation. So typically you're interested in the Poisson equation. And remember, what the Green's function does for you is that if you know how to solve the homogeneous differential equation, Green's function helps you to solve the inhomogeneous differential equation. Okay, so that's the idea of Green's function. And what it does is that since the Green function requires only a particular solution, so it looks for a solution for a point charge. So you write down the Green's function then, right? So Green function or Green's function. Right. So let's also, so each differential equation, every inhomogeneous differential equation, remove the source and replace it with a delta function. That's called the Green's function associated with the differential equation. So in that sense, this will be the Poisson Green's function, and that will be defined as negative del square. So instead of the electric potential due to this source, so notice what I'm doing. I take the differential equation, replace the quantity I'm interested in with the Green's function. But now the Green's function depends both on the observer and the source. I'm introducing a source. The delta function source, delta cube or prime. And probably it's a good idea just to keep everything with the same dimension so that G has the same dimensions as phi with unit magnitude to introduce an epsilon naught also. This is just for the SI units, right? We are working in the SI unit. So the best place I think, at least from my experience, is to introduce that epsilon naught here. Otherwise it will float around inside the Green's function. Okay. So that's your Green's function equation. And since this is a math methods course, I'm going to kill this. Okay. So the G that shows up here may not match with the G that shows up in E&M. I'm not sure whether that's the right thing to do or not. Will it be confusing? Why not? Just put an epsilon naught. Yeah, let's keep it consistent. So that's the equation we want to deal with. That's minus del square epsilon naught just sticks with G. It's a spectator that sits right behind G all the time. We'll carry it with it everywhere. Right? So that's equal to the function okay. Any questions regarding the motivation for Green's function? What it is? Okay. And of course, the solution for this is, we know, right? Based on experience, we know that this is indeed 1 over 4 pi and 1 over r minus r prime. Okay. Since there is only r, the dependence is of the form r minus r prime, often this is written as r minus r prime here. That shows us that this is having a translational symmetry between r and r prime. Let's do one thing. So now we have three.
Can I ask a quick question about the greens?
Uh-huh.
If we can say that greens is equal to 0 if we're on the boundary of the, or is it not equal to 0 still? I'm just trying to think, like, when would this equation be equal to 0?
This equation, you mean here?
I can't see what you're pointing at because you're standing in front of it. But
This equation, you mean?
yes.
This is 0 whenever r is not equal to r prime. Okay, notice maybe I should clarify that this comes out much more clearly in the exam problem that you're doing. There we really have a material, right? So typically how the problem will work is that you have a conductor here, right? You have another conductor there. And once you have a conductor, your all the electric field has to be 0 inside. So you're confined in a cavity in this region. And then the question comes, oh, what is your potential on the boundary? So those questions come in, correct? So then you have to say that, oh, this conducting body is grounded so that it is 0. Right? So that's one way of doing it. But now at this point, this is much simpler. We have just one point charge in the whole of the space. In the whole three-dimensional space, we have one point charge. That's a charge density, right?
Yeah.
So we have one point charge and nothing else. And there is a boundary at infinity. So you can ask what happens to the boundary electric potential at infinity, and you require it to be 0. So yes, there is every differential equation, you have to specify the boundary conditions. So here we are saying, so let me, maybe since you asked, helps me to clarify, always a differential equation should be given with its boundary condition. So let's say that phi limit r tends to infinity, magnitude of r, not the vector, of phi is equal to 0. That means everywhere in space. Is that what
That's exactly what I was asking. Yeah.
yeah. And that is satisfied by this equation, if you know, since it is 1 over r. Gets satisfied. It is slightly more like I have sort of hand waved this. If you really start from the very scratch, the Gauss's law is more important. So you have to be able to capture this, and you should get back your charge every time you integrate them. And we tried to emphasize that, or I tried to emphasize that every time whenever we were doing vector calculus. If I have a surface around this point charge, I should be able to capture the divergence theorem should be satisfied in that case. So that's another way of saying it. So that 1 over r has a meaning. It's very. It is very necessary that this has to be 1 over r. There is no other form possible. It's not an approximate or guess, something like that. Okay. Okay, if I proceed with that, so again, we are looking for this differential equation, which is the electric potential for a single point charge in the whole of space that satisfies phi going to 0 at the boundary, and that's the solution for it. So one way of saying this is that, oh, I know G, so I'm done. I don't want to worry about it from this point on. I don't want to do anything new. But it's good to explore this more. One simple thing you could do is that, what's the Fourier transform of this? Right? So you have a function here. What is a Fourier transform in all of 3 spaces? There is a translational symmetry there. So it seems like, why not do a Fourier transform, and it might be useful, right? In Fourier transform, we have noticed that things get algebraic, right? So let's ask, what is the Fourier transform of G? So, G of epsilon naught, right? It has to sit right next to it all the time. R minus R prime. So you guys say that I always block your view when I'm writing. So I should learn to look at the camera instead of the computer screen that I keep watching. Okay, so epsilon naught G. Since there is this R minus R prime dependence, it seems to suggest that we can write a simple Fourier transform for this. So let's define the Fourier transform to be all going from, so this is minus infinity to plus infinity dkx over 2 pi, so minus infinity to plus infinity dky. So in all three spatial directions, and dkz over 2 pi minus infinity to plus infinity. And we have e raised to ikx times x for the x coordinate, e raised to iky times y, and the y coordinates e raised to ikz times z, and the z coordinate. And the Fourier transform of this, let's call that, what should I call it?
What are you transforming to? You're going from,
I'm going from the position space to the wavelength space. Like
Okay.
if it is a time dependence, I will go into the frequency space.
Mhm.
Since this is a position coordinates x, y, z, I will go into the wavelength space, like, or momentum space, if you want to say, k. Right? If you are Fourier transforming time, you get frequency, right? And if you're Fourier transforming x, you get k, right? Which is the wave number, right?
Mhm.
So that's your kx, ky, and kz. And this one, let me just call it epsilon naught g tilde. And this quantity, this will depend only on kx, ky, and kz. That's of course when I explicitly write all the coordinates x, y, and z. This is much. Oh, I should be careful. This is x minus x prime, right? Sorry. So this should be x minus x prime. That's y minus y prime, and that's z minus z prime. This is often written in this following form: d cube k over 2 pi cube, right? So d cube k means dx, dkx, dky, dkz. Exponential, this is the dot product of k and x minus x prime. So that's I times the vector k dotted with r minus r prime. And this is your Fourier transform. And let me forget about the tilde. We will understand that whenever this is a k-dependent quantity, that's a Fourier transform. The two Green's functions are not the same. Is that clear?
Yes.
And of course, you would like to solve this, correct? If you want to find this, what will you do? Green's function is determined by this equation. I will substitute this in there. I'll do one more thing for that, keeping that in mind. The right-hand side of this equation is a delta function. So I also know that delta function, each of the delta functions, so let's say, first let me write x minus x prime is equal to dkx. What's the Fourier transform of a delta function?
One.
Yes, it's 1, correct? Very good. Right. So Fourier transform of a delta function is just 1. That's e raised to ikx times x, just 1. So I can have 3 delta functions there. So instead of x minus x prime, I'll write 3 of them. That's r minus r prime. That's equivalent to delta of x minus x prime, delta of y minus y prime, delta of z minus. The 3 delta functions there. Change this to d cube k, 2 pi cube, and change this to k dotted with r minus r prime. And it's 1 again. Okay. So I can substitute these two forms into the differential equation, and I get minus L squared times the whole Green's function a Fourier representation, which is an integral representation. So that's d cube k over 2 pi q I k dotted with r minus r prime, and we have epsilon naught times g of k. Is equal to delta function, but the delta function is again cube k over 2 pi cube as 1. Let's operate this delta function because I would like to match these two from the left and the right. At this point, I cannot match it because this has to act on it, right? It's very clear what is the coefficient of this, because this derivative operators actually act on this Fourier eigenfunctions. So let me operate this gradient operator on the exponential. So what is the gradient operator acting on e raised to ik dotted with r minus r prime? What is that equal to? Notice this acts only on this r, correct? That's the only place where it acts. So this gradient does not see any r here. That's the only place where it acts, this place. And that's this. So it just brings down an ik vector. And gives you back the, that's your derivative operation, right, of an exponential. Is that clear? Any questions on that? If I were to operate this again to get del square, again it will get only this r, right? So it will get you this r and again give you an I taper. That's all it does. So in the Fourier world, derivative operators are very easy. Just replace all the derivatives with wave numbers, 1 over wavelength, and you get, so this is minus k squared times ik dot if I were to use this in here, I get the equation cube k over 2 pi cube exponential of I k dotted with r minus r prime minus of this and the minus in front of the Laplacian cancel out, and I have k squared times epsilon naught times the Green's function in the Fourier space equals the right hand side, which is actually having coefficients 1 other than the Fourier eigenfunctions. The coefficients are just 1. Whenever you have two Fourier series equal to each other, their coefficients has to be 1 because Fourier functions form a complete set of functions. So we learn that the Fourier transform that we are interested in, with an epsilon sitting in front of it, we decided to carry it along, is going to be just equal to 1, which has a very simple solution. So we found the solution for the Fourier transform. That's just 1 over k squared. So the Fourier transform of your electric potential for a point charge in the momentum space is simply 1 over k squared. If you analyze the problem in the Fourier space, that's what it will come to, which means that, so this is your equation, right? This was your defining definition here. So let me remember what we are doing. Epsilon naught.
Sorry, I may have missed you say what happened to the negative sign.
The negative sign, there was a negative sign in front of the Laplacian, and the Laplacian itself had a negative sign. So the negative and this negative cancel out, right?
Yeah.
Because it's negative del square that's going to operate, so that makes it a positive. So it's just k square times that. Right? So nothing. Right. So what we have learned is that our Green's function, which is the electric potential due to a point charge in this context, has a representation which is called the Fourier representation, which is an integral slightly misleading to say this is an integral because this is like a series, right? This is a Fourier series, like a series expansion for sine. Similarly, this is a Fourier expansion of this electric potential, and its coefficients are 1 over k squared. Right? It is this piece that is important. And often you don't try to evaluate this, right? A Fourier series is left out like that. These are sort of the eigenvectors or eigenfunctions associated with that expansion. So its components are 1 over k squared. But it's a good idea to verify. So this should be an identity then, right? There should be an identity that if I were to evaluate that integral on the right hand side, I should be able to get the left hand side again. So that's a good exercise to do. And that's what I think yesterday Moses was trying to suggest in some context. So let's try to verify that this is indeed true. So what we have done is that we started with a definition of Fourier transform, substituted in the differential equation, got this 1 over k squared. So let's finish the cycle. That means to say that if I were to evaluate this integral, I should get this left hand side. It should be an identity there, right? So let's see if that is doable or not. So let's evaluate this integral. This is d cubed k over q pi cube, and that is e raised to I k dotted with r minus r prime. And let me temporarily call this r minus r prime to be a capital letter r, right? Vector r is equal to r minus r prime. A temporary definition. That's vector r, and that's 1 over k squared. Let's work in the spherical coordinates with respect to k. So there is a k space. So we have a coordinate system here, right? So this is k, vector k. Right? So this is kx, that's ky, and that's kz. That's kx, that's ky, let's say. And that's your vector k. And in this space, there is a constant vector r. So since I am working on only this integral, I can make a choice that I will choose my r, I'll rotate my coordinate system in such a way that r is chosen to be along the z-axis. Since I'm not doing a very general problem, I'm confined to this particular problem, I have a choice in the coordinate system. That's my vector r. So that's a choice. I choose my kx, ky, kz. I rotate it off so that kz is in the direction of r. And then using spherical coordinates, that means that this will be angle theta, right? Remember, theta phi is done in position space, but kx, ky, kz can be imagined to be, there's a one-to-one correspondence between those coordinates and this. So that's equal to, in spherical coordinates, we have 0 to infinity, and this is dk. Right? This is now the radial coordinate of k, and there is an angular coordinates which goes from 0 to pi, and whose distance is k times d theta. Same as spherical coordinate, except that k is being used for r. Right? So in this case, I'm having k theta phi. So there is an analogy of this with r theta phi. That's just an analogy. This is not really the position space. That's a momentum space. And f0 to 2 pi, k sine theta d theta d phi. I'm writing it in this form. Often this is written as k square d theta, k square sine theta d theta d phi. The angle between k and r is theta, so it is cosine theta. So this becomes e raised to I k r cosine theta divided by k squared. Is that clear? Any questions? Okay. Clearly, the k's cancel out. that's a simplicity. And there is no phi dependence. So the phi integral can be done immediately. So I get phi integral gives me a 2 pi. And what I'm left out with is 0 to infinity dk and 0 to pi sine theta d theta and e raised to I k r sine theta. Substitute whenever we have an integral like this, that it's a function of cosine theta, it's good to substitute cosine theta is equal to t. So that this becomes minus sine theta, d theta is equal to dt. So we have 2 pi. Keep the k integral intact. Then when theta is equal to 0, t is equal to plus 1. And when theta is equal to pi, t is equal to minus 1. Sine theta d theta is minus dt. And we have e raised to I k r times t. The minus sign that shows up can be used to flip the limits of integral, which in the more traditional form, which is minus 1 to 1. And then the integral is doable, right? At least the theta t integral is doable. That's just an exponential integral, convenient. Right? And it doesn't go to infinity and all, so it's a very simple integral. Let's do that. It's 2 pi t e raised to I k r. So it is the integral is e raised to I k r t divided by I k r. And this has to be evaluated at t is equal to plus 1 and at t equal to minus 1. Which gives me so this, let me introduce a 2 here, 2 there. So let me write this as 2 pi times, let me pull out an r from there. So I introduced a 2 I so that I can recognize that as a sine function. Actually, let me not pull out a r. So this is 2, 0 to infinity dk. And that's nothing but sine of kr divided by kr. And I'm missing some things here, right? What's the mistake I made?
So can you explain to me where the 2 came from again? Because you have e to the.
I wanted to remember sine of theta is e raised to I theta, like e raised to I theta minus e raised to minus I theta over 2 times I, correct? So I wanted to see that 2 there right away. right? These limits give you e raised to ikr and minus e raised to minus ikr. And that I put a 2 in there and then a 2 there. Is that clear?
Mm-hmm.
Yes or no? Should I?
No,
increase it?
yeah. I mean, I got you. What you did there.
So, but I made a mistake. I dropped something. Can you guys detect in the very first line here on the board? I missed something. Notice that there was a 2 pi cube, right? When I used the spherical coordinates to write that, I forgot the 2 pi cube completely. Right, so that's sitting right in front of it all through. So that's 1 over 2 pi cube. Is that clear? So that was a mistake on my part. So that goes through all through. So that's 2 pi cube, 2 pi cube, 2 pi cube, which of course cancels one of the 2 pi. That's there. So that's 2 pi cube. So that's a 4 pi. So there's a 2 pi cube. So now let me do that in the next step. It's 2 pi cube. So 2 raised to cube is 8. That is a 4 in the numerator. So that is a 2 that shows up in the denominator. So it's a 2 pi square, right? So this is equal to 1 over 2 pi square. So let me write this as 4 pi and then 2 over pi. Just a fancy way of writing it. I also want to substitute kr as x. So this kr gives you an x, and that's equal to then 1 over 4 pi r, and then there is 2 over pi, and 0 to infinity dx sine x over x. Okay. What's that integral equal to? This was in there in one of your homeworks, I suppose, in contour integrals. What's that integral equal to? It turns out that's exactly pi by 2. Okay, so that's, but that's not easy to evaluate. You cannot do it using, or maybe I gave you as an extra credit problem, right? That I think, yeah, once I gave an extra credit problem asking you guys to check if this can be done using elementary methods. But this is pi by 2. You can show that using contour integrals for sure, and probably using some standard tricks. So this is equal to 1 over 4 pi r. And r, remember, was r minus r prime, so it is 1 over 4 pi times 1 over r minus r prime. So indeed, it's had to work, right? So this is indeed true. So that's a Fourier series, Fourier electric potential due to a point charge or the Green's function. But in your exam, midterm 3, you analyzed a problem where you're doing Fourier transform only in the x and y coordinate. Right? And so you could also ask, what if I don't do the Fourier transform in all three? I do only the Fourier transform in two directions, which is perpendicular to the z direction. So I choose my z direction to be special, right? And that is usually advantageous when you're doing planar symmetry problems. But at this stage, let me just motivate it by saying that I do Fourier transform in two dimensions, right? X and y. That's also reasonable. And this time it will be k perp dotted with r minus r prime perp, right? This is whatever shows up in your exam, right? X and y.
So you still have a 2 pi cubed term?
Oh, sorry, not 2 pi cube, 2 pi square. Is that what your question is?
Mm-hmm.
Yeah, 2 pi square. Thank you. And whatever is the Fourier transform, we will write that as epsilon naught times g. This time it will depend on z, right? Z comma z prime comma k perp. But it turns out that you can solve that again, and that's part of your exam. And this comes out to be 1 over 2k perp times exponential of minus k perp. Notice this is not oscillatory. This is a decaying function. So that's your solution, and that will be an epsilon naught somewhere, right? No epsilon naught, because epsilon naught is on the left hand side. That's also a solution, right? And I won't go into the details of that at this point of where that is coming from. And generalizing this, I did Fourier transform in 3 directions. I did Fourier transform in 2 directions. One could always think of Fourier transforming in 1 direction. Yes, that can be done. But at this point, let us try to work with this. Like, can we do something here? And that is where Bessel function is. So let me try. So here, what we did earlier was that we started with this expression and try to do the k integral. Let me now start with the last expression I wrote down, and again try to do the k integral. But this time I'm in 2 dimensions, so cylindrical coordinates are better. So let me again do the same exercise. So this was r minus r prime. So let me define a vector p, which is r minus r prime perp. Right. This is the x and y components of your vector r minus r prime. So this is the projection of r in the xy plane. So then I have epsilon naught g this is just a way of introducing the Bessel function. I'm not highlighting the motivation too much. So this is d2. So this is d2k perp over 2 pi square times e raised to I k perp dotted with p. P becomes a constant vector now, and I have e raised to minus k perp z minus z prime over 2 k perp. You won't complete the evaluation, but let's see k perp, this integral there. And again, like earlier, I have a two-dimensional space, which is kx and ky, and there is an arbitrary vector k-perf, sorry. Right. And I have to integrate on all those vectors in that plane. So cylindrical coordinates is good, but there is a vector p here. In general, it is anywhere, but I can choose it to be in the x direction. Let me choose my p to be in the x direction. And let's choose this angle to be alpha. So cylindrical coordinates typically is done in rho and phi. Right. Instead, now let's say this is k per magnitude of k per, and phi is alpha. So if I span my k perp and alpha, I get the whole plane. So that integral d2k, so that means that epsilon naught g of r minus r prime, which is p actually, correct? So I can write this as p. So this is p. No, not p, sorry. So this is dependent on p and z minus z prime. So let me just say r. Right. That's equal to two integrals. Before that, I pull out the 2 pi square. Do not forget it like last time. And this is 0 to infinity dk per, and 0 to 2 pi d alpha, but with the arc length to be k per. That's your integrals, and I have e raised to I k per p times cosine alpha. That's the angle between them. Correct. The k perps cancel out. If the k perp cancels out, and I can bring out the 2, right? There's a 4 pi square, so let me write this as 4 pi, 1 over 4 pi. There's an epsilon naught already in there. And then I have 0 to infinity k per. There's an exponential, let me bring it in. And the alpha integral seems to be this. Okay. Any questions until this stage?
Can you just read out that last integral? It's a little bit blurry for me.
Oh, it's not readable. Oh, let me use another. Oh, there. It's getting light, huh? Let me see if this is. Oh, this is also not very good.
I think the mark is fine. It's just like my zoom is making it blurry.
Oh, okay. So let me rewrite it then. Okay. Is there any reflection coming here? Sometimes light reflects. nothing here, right? So I can write it there.
Yeah, it's okay.
This is equal to 1 over 4 pi 0 to infinity dk per, one of the k pers cancelled out. I pulled in the exponential with the z in it, the decaying z minus z prime exponential. So it is exponential of minus k per magnitude of z minus z prime. And there is the alpha integral 0 to 2 pi the alpha e raised to I k per p cosine alpha. Correct? Helps?
Mm-hmm. Yeah, thank you.
So this is very much in spirit similar to what we did earlier. There was a k integral, there was an angle integral. We did the angle integral, we got the sine theta, then the k integral was due. Correct? So we should try to do the angle integral. And what's the angle integral? Exponential of I k per cosine alpha. What's this integral equal to?
You do the substitution, right?
Yeah, but last time, remember, we had the sine theta in front. So at that time, you make that substitution.
Oh, yeah. Yeah.
Right? So this time, that's not a very good substitution.
I guess you just do. I mean, nothing in the E is dependent on alpha, is it? Or is that cosine alpha? I guess.
Yes, that's cosine alpha. The angle that you are integrating on is the same as cosine angle.
Okay.
Right? That integral is not doable. Okay, that cannot be done. Whenever you cannot do an integral, you just give it a name, right? And that's your Bessel function. Okay, so this is your Bessel function. So you define this as 0th order Bessel function. Let's call it, introduce a t there. Right? So this is equal to, oh, that was a 2 pi. The second time when I was writing, I missed a 2 pi. Right? There was a 2 pi square for 8 pi square, right? So 4 pi went there, 2 pi there. So I introduced a 2 pi in the underneath d alpha. Okay, sorry about that. So you define this to be a Bessel function. So Bessel function is defined as 0 to 2 pi, the alpha, an angular integral, and its argument is t, so that shows up as k per p, and cosine alpha. Right? So this is only one of the Bessel functions. This is 0 sitting there, so it's called the 0th order. Remember your legendary polynomials? There were many legendary polynomials of order L. So this is called the 0th order. Bessel function. And of the first kind. What does it mean by first kind? Whenever you have all these functions are typically solutions to differential equations, you'll find the differential equation for the Bessel function. And whenever you have a second order differential equation, it satisfies two solutions. This is one of the solutions, right? And not only one, there are many of them. Out of the first kind, this is the 0th order. You're going to find J1, J2, J3, J4, all those, but all those will be derived from this fundamental representation, integral representation. So this is an integral representation of the Bessel function. Typically, more traditionally, you would write a series for this. How would you write a series? You want to do this integral, you're stuck here, you don't know how to do this integral, but there is cosine alpha. So you will write a series for cosine alpha, right? Whatever that series is, after you expand it out, each term of that series can be integrated out. Whatever remains will be a series that will be called the Bessel function, and we will derive that series, okay? So at this stage, let's start by saying that's Bessel function. So the motivation is clear. Point charge or point charge or a point mass in gravitational physics or in electrostatics was studied too well. So it is encountered when you Fourier transform in two directions. And when you have an integral consisting like this and you want to really use it again and again. So you give it a series representation, but you find a lot of properties associated with it. Why? Because it is so important. You can start with any integral and do the same thing, but most of the integrals are not useful, so no one explores it so much. Okay, so it's just an integral. Bessel function is just an integral, which we cannot do using elementary methods. That's all. And of course, it's a complete, it forms a complete set and all those features are there. But at this stage, it is just a definition. Any questions, comments? That's all I have. It's a very quiet.
Just thinking.
Good. Mhm.
So
Okay,
you
thank you.
typically modify or you typically talk about the Bessel function of the first and second kinds in terms of the series itself.
Yes. Like traditionally, if you go, you will see a series. And what is that series? Basically, you expand cosine alpha as a series. Right? Once you expand that and then expand the exponential, so it's a double series in that sense, you will, each of term in that series can be integrated. But it's a series. So, and it's a double series, then you identify your, so we'll do that next time so that you're clear what I'm talking about. And that series is a good definition. And usually that is how you work with Bessel function. So you derive lots of identities. First thing you do is talk about what is a recurrence relation. Then you show that these are orthogonal functions so that you can write any arbitrary function in terms of these functions and so on. Like most of what we did for legendary polynomials can be done, or not just can be done, is done for Bessel function.
Okay. All right, thank you.
Okay, you're welcome.
Thank you.
Goodbye,
Bye.
Michael.
Have a good day.
Bye, Jordan.
See you guys.
Yeah.
Let me close.